till my shadow turns to sun rays, and on we'll go through the wastelands, through the highways, and on we'll go. And we'll grow in number.
Okay, hi. I'm TAMARA BRODERICK. I'm a professor at MIT, and today I'll be talking about using variational Bayes for scalable Bayesian inference. And I believe I'll be talking about this for a few more lectures, so we'll do one today, and then we'll do a few more in the coming days. I'll also mention, of course, I'll be sharing my slides with the awesome summer school that's hosting. I'll also be putting them up at the website at the bottom here. So they're not up yet. I'll be putting them up after each presentation, but you can find them there. So I just wanted to point you to that. Okay, so I said we're trying to do scalable Bayesian inference. So let's just motivate, why are we doing that? I have personally found that I feel like whenever there's a big scientific discovery, or scientists are working on some really important thing that's going on in the world, it just seems like it's almost always the case that somebody's using Bayesian inference in that work. And so the sort of elephant in the room right now, as an example, is of course coronavirus or COVID-19. And if you look at this, if you look at sort of the research that's been done in this area, there's just a huge amount that's using Bayesian inference. I'll just mention sort of a couple of things, but this is really just the tip of the iceberg. So for instance, people have been interested in the so-called serial interval, roughly the time between successive cases as a disease is transmitted, and Bayesian inference has been used for that. That's one of the papers here. People have been interested in understanding the effects of interventions like lockdowns or schools closing, and that's two of the papers here, and Bayesian inference has been used in both of those. Of course, again, there's many, many more. Now, some of the scientific discoveries of the recent past, perhaps, are a little bit more fun to talk about. So one of these is the exoplanets discovery, the discovery of these, exoplanets in the TRAPPIST-1 system. Really exciting discovery. And in this case, Bayesian inference was used to get point estimates and uncertainties of candidate observations to determine which ones could be safely categorized as exoplanets. And I should say, in the previous example too, with coronavirus, people are interested in, again, not just estimates of things like the serial interval or the effect of lockdowns, but uncertainties as well, to know, are we really sure that these things are working, or that we know what we think we know. Another big recent discovery was the discovery of gravitational waves. So here, Bayesian inference was used to figure out things like point estimates and uncertainties in things like the mass and spin of the black hole that was emanating these gravitational waves. Tragically, in 2009, an Air France plane crashed in the Atlantic Ocean, and for many years, people were trying to find the wreckage. It's really important to find sort of the black box and understand what happened in these cases so it never happens again. And there was just no luck. And then, a couple years in, people brought in somebody practicing a form of Bayesian inference, and they were able to find it in a couple of weeks. Now, of course, they had the information from these previous searches, but that's still pretty exciting. When you are interested in something like understanding, how are you going to route maybe an ambulance to help somebody who has some really, serious health problems and they need hospital attention immediately, you're really interested in not necessarily just point estimates, but uncertainties. Let's say you're deciding between route A and route B, and route A takes on average, let's say 9 minutes, and route B takes on average 10 minutes. You might think, route A sounds better. Let's get to the hospital quick. But maybe you need a life-saving procedure in 13 minutes, and suddenly 9 plus or minus 5 might look worse than 10 plus or minus 1, just because you're certain to arrive at the hospital in time. Now, also in the social sciences, economists like Rachel Meager have used Bayesian inference to understand things like microcredit, these small loans to individuals in impoverished areas. And we really want to know, are they effective? Are these actually helping people get out of poverty? There's also things like Hamza Balakrishnan at MIT has studied planes and understanding their fuel usage based on their routes. And so this can be really useful for, improving fuel usage, for understanding, what's happening, maybe even regulatory purposes. Fishery management is another case where we really care about uncertainty and risk, because there's this risk of potentially losing all of the fish, a population of fish. And so this can be really useful in this case. Okay, so here's just a ton of examples. And again, this is just a few, there are many more. But I think one thing that we can see from this set of examples is, what are we trying to get out of Bayesian inference? And I think what we're really seeing in these examples, at least, is that we want point estimates of some unknown quantity. We want an estimate of that quantity. But we also want to know not just what do we know, but how well do we know it? So this is super important for science, but also more generally decision-making, in engineering, and so on. Okay, and then of course there are other reasons that people use Bayesian inference as well. It can be relatively interpretable in the sense that you can specify exactly the parameters that you're interested in, and then try to learn the values of those parameters. It's modular, so if you have an idea of sort of how physical processes work, or how various components in a process fit together, you can encode that, and that can be useful from a practical standpoint as well. And sort of more generally, you can encode expert information in various ways. So certainly in all of these cases, there are a number of experts that already exist. They have a lot of expertise that we would like to encode in the problem. And that's certainly something that you see in all of these applications. Okay, so not only is Bayesian inference very widespread, but there are excellent tools for it these days. This is a super non-exhaustive list of the amazing probabilistic programming languages that are out there. Just a couple of examples. Our TensorFlow has a really nice probabilistic programming language. Stan is extremely widely used. I think it's downloaded something like tens of thousands of times every month, and actually I think that's pretty old information at this point. I think it's even more widely used than that statistic might suggest. Okay, so that all sounds really great. Bayesian inference is used all the time, and we have this probabilistic programming languages that do it really well. And so what's the problem? Is everything solved and we don't need to keep talking? Well, no, there are a lot of challenges to Bayesian inference, a lot of practical challenges in person. And so let's say, what are three sort of goals that we really want for Bayesian inference? Well, one, of course, is compute speed. So if I'm doing a study on coronavirus, and this data comes out in March, and I really want to get my study out to save lives immediately, I don't want to have to wait a month for my Bayesian inference to run in order to even be able to see the result. And then personally, I find that anytime I do any form of machine learning, I run my code, and then after I run my code, I realize that there were bugs in my code. And so then I have to run it again, and so on. And so it's not like one run is your real cost. It's really like you have to run that multiple times. And so anything that costs a really large compute time is going to be prohibitive. And we can just really see in some of these examples that that's going to be a real problem for those applications. Okay, now something that I think is really important to keep in mind is that compute time isn't the only time that we care about. User time is a huge part of timing. So, let's say that, you're a biologist, and again, you're interested in some study of coronavirus, and, your compute time is super fast, but it's going to take you 6 months to derive equations to do anything. Well, again, that's not good enough. We want somebody to be able to do their awesome science that saves lives, or gets at some really cool scientific discovery, and we don't want it to take 6 months or a year, especially in these time-sensitive situations. And so their user time really matters as well. It's something that we have to keep in mind. And then finally, of course, we care about reliable inference. I can easily come up with an algorithm that is fast in compute time and fast in user time. And here is my algorithm. It returns the number 6. It's super fast. It's literally constant time. You can't get much faster than an algorithm that just returns the number 6. It's fast in user time. There's no tuning. There's nothing you have to do. But I think this example illustrates why you have to be skeptical of something that just says it's fast, because it's easy to just be fast. It's hard to be fast and accurate. And so that's why we really have to, whenever we talk about speed, we just have to simultaneously talk about quality. What is the quality of the inference? And so this is the real challenge, that there are a lot of methods that are out there right now that are really high quality, but are extremely slow. And likewise, there are methods that are very fast, but may not be so high quality. And so how do we get Bayesian inference that is fast and high quality and supports all of this awesome science and engineering that people are doing? That's the real challenge that we're facing. And I think it's just really an open challenge. So today we're going to talk about variational Bayes as one of the methods that people have suggested for addressing this challenge. And before I go on and talk sort of more specifically about variational Bayes as a potential solution, I do want to just mention there's this sort of point that sometimes comes up, and people think that, well, do we even need Bayesian inference for our modern very large data sets, because doesn't uncertainty just disappear? And I want to push back on that a little bit. Because I think if you have a very large data set and all you care about is one parameter in that data set, like an average of the data set, then yes, absolutely, it disappears. But I think that's not the way that we interact with our modern very large data sets. If you think about a giant data set from Amazon or Walmart, it's not just that you have these purchases that people are making for products that everybody is purchasing, but you have this extremely long tail of products that not everybody is purchasing. Same thing if you think about something like Uber data set or traffic data set. Yeah, there are some roads that everybody travels on, but there's still uncertainty from different times of day, and there just being noisiness there. But also there are roads that are much less traveled on, and we still want to be able to say something about those. And so I think in general, when we have very large data sets, it's not just that we're asking a single question and we get more and more data about that question, it's that we're asking more questions. And that's what retains the uncertainty that we have. Okay, so that's a Bayesian inference setup. This is why we care about Bayesian inference. And so now we want to think about, what are ways that we could address this challenge that we talked about, getting speed and accuracy at the same time. And certainly variational Bayes is one of the proposals out there for dealing with this. So as we just said, modern problems have both not just large data, but also large dimensions. And this is really where variational Bayes excels, at least in certain ways. And I think just the thing that is really the selling point for variational Bayes is that it can be extremely fast. And so for that reason, we see that it's used on essentially modern very large data sets. So giant text corpuses have just been a huge point of interest for variational Bayes. Increasingly, we have tons of data on networks, like social networks get very, very large. Neuroscience data can get very large, especially very high dimensional. And then various forms of biology and genomics data also get very large and very challenging. So these are all cases where people are using variational Bayes. They're using it because they have such large, challenging data sets. And so we'd like to understand what's going on with variational Bayes. I think a very general lesson in machine learning is that there is no perfect machine learning algorithm, but these are useful tools in a toolbox. And so for every algorithm that you encounter, you should ask yourself, what are the benefits of it, and what are the things that you should be aware of, that might be some failure modes? And everything has them, and so you want to figure out what those are. Okay, so today we'll start by going into a little bit more depth in what exactly are we doing in Bayesian inference, and what does it mean to be doing approximate Bayesian inference. Then we'll start defining what exactly is variational Bayes. And it turns out there's a particular form of variational Bayes that's extremely widely used. If you just read a paper about variational Bayes or that's using variational Bayes, there's a really good chance that it's what's known as mean field variational Bayes. So we'll say what that is as well. And then we'll talk about why should you use variational Bayes, like what is helpful about it, what are its benefits, how does it work in practice? And then we'll talk about some potentially pitfalls. As I just mentioned, I think every method has some pitfalls. Just because you don't know what they are doesn't mean they don't exist. And so we should ask ourselves here, as in every other method, when can we trust this? And are there any downfalls? And then we'll talk about where do we go from here. Now, I want to mention, and we're not going to do all of this in today's session. We're just going to get started in today's session. But by the end, we'll have addressed all of these points. Okay, so let's start with this review. Just reviewing what is Bayes and what is approximate Bayes. Okay, so Bayesian inference, we're interested in some parameters. These are the unknowns, the things that we're interested in learning about, like for instance, the serial interval of coronavirus or the mass and spin of the black hole that's emanating gravitational waves. It's something we don't know, but we want to know about. We start off with a prior in Bayesian inference. This is sort of expressing what do we know going into the problem before we've seen any data. Then we will collect some data. Now here, I'm just having sort of a cartoon of Bayesian inference. And it's worth recognizing what's a cartoon about this. We as humans can only see in 2 dimensions. And so here I'm plotting essentially a 1-dimensional parameter. But of course, in real life, we have these very high-dimensional challenging parameters. And so, take this cartoon with a grain of salt, but I think it gives at least a little intuition. Okay, so we collect our data. Let's call our data Y. We'll say that our data is Y1 up to Y capital N. So we have capital N data points. And we're going to abbreviate that as Y1 colon N for our data set. Our likelihood will be the probability of the data given the parameter. So this sort of describes how the data might be generated if we knew the parameter value. And then finally, the idea of Bayesian inference is to calculate the posterior. So if the prior is what we knew before we saw any data, the posterior is what we know after having seen the data. And the cartoon here concludes sort of saying, okay, we applied this fact of probability, Bayes' theorem, that relates our data and our parameter, and we learn something about the parameter. And the way that we can express that is that our uncertainty has decreased, sort of the width of this distribution roughly has decreased. And now we have a better idea of sort of what is the parameter value. Okay, so how do we use Bayes in practice? Well, there's essentially 3 steps. So the first step is you have to choose a prior and you have to choose a likelihood. That's essentially those 2 things together form a model, or what might be called a generative model. Now, this could be an entire lecture series on its own. And so I want to say this is like a really challenging and important set of questions, and it's just not what we're going to get into today. I'm going to assume that we have a model that some scientists have consulted with us and come up with a super cool model. And we're going to focus on the next steps in Bayesian inference, which are we have to now, once we have our prior and our likelihood, we can compute the posterior. All you need is the prior, likelihood, and data to do that, because it's just, again, Bayes' theorem. And then we're going to report a summary. So the reality is, whenever you're using Bayesian inference, you pretty much never report the entire posterior, especially if it's in high dimensions. You just can't visualize that or think about that. And so what you'll typically see in a paper is that somebody reports some notion of a point estimate and an uncertainty. And an example of that would be the mean of the posterior distribution, perhaps in each dimension of the parameter, and some sort of variance or covariance. Okay, so as I said, we're going to focus today on steps 2 and 3, which is not to say that step 1 isn't challenging, it's just a different kind of step. But steps 2 and 3 are challenging from a computational perspective. So let's talk about why that's the case. Why are steps 2 and 3 hard? Well, there's typically no closed form for the posterior. Yes, this is just a simple fact of probability. And once I have the prior and the likelihood, the posterior is defined, but can I actually get it? Can I actually use it? Can I report a mean and covariance? In general, there's just not going to be a super simple equation for that. So I have to approximate it somehow, or do something to get at that. But I can't just solve for it either. So there's a high dimensional integral that's going on here. And I need to think about, well, what can I do to get at that integral? And so let's just talk really briefly about why there is a high dimensional integral. So in particular, well, one, if I'm trying to do this integration, if I'm trying to figure out, oh, I think that my other, the second me on this chat may have been kicked out. I don't know if that's possible to get back in. But so continuing here for the moment. So we have this this integral, and so part of the reason that might arise is because we have we need to do a mean, we need to do a variance, and so those are going to be things that involve an integral. But also, even if we just look at this equation to begin with, we have also, I think somebody may have drawn on this. I don't know if that's possible to get rid of. But if we're just solving this equation too, we can look at what is the normalizing constant. That's just the probability of the y here. And how do we get the probability of the y again? Because all we have access to here is the prior and the likelihood. And so from that perspective, we need to do is we need to derive it from the prior and the likelihood, and that's just going to be the integral over theta. So this is the joint. We can get that from the conditional and the marginal, and we can get that by doing this theta thing. Again, I don't know if there's any admins in the room, but if it's possible to remove that drawing, that would be super. Great. Okay, so we have this high dimensional integral, and the question is, how do we solve it? So now we have to think about how to do that. Okay, so there is a gold standard for this that's so-called Markov chain Monte Carlo. It's been used for decades. I mean, it really made Bayesian inference something that we could actually use in practice, and that's been fantastic. And so what's great about it is that it's accurate if you run it for long enough, but you can sort of immediately see the problem that long enough might be really difficult. And so, this could be too slow to really run in practice. And so this is sort of the big reason that people are looking for some alternative. Thanks for getting that. This is the big reason that people are looking for some alternative. They want something that that they can run in the time that they have. Okay, so now if you think about modern machine learning, like what are people doing in modern machine learning? What are sort of the types of approaches they're taking? Well, so one of the sort of like hot things in machine learning right now is optimization. There's this feeling that optimization is really fast, that it's something that we can use to speed things up. And so one idea here is to say let's not use Markov chain Monte Carlo at all to approximate our posterior. Let's try using something else, like maybe could we use optimization? So here, remember our posterior is a distribution over theta. And so could we approximate it with some other distribution over theta? Let's call it Q star. And so the basic idea here is imagine that you have tons of different distributions. This is sort of the space of distributions. And some of them are nice. What do I mean by a nice distribution? Well, the types of things we're trying to do at the end of the day are we're trying to report posterior means. We're trying to report posterior uncertainties. Maybe we're trying to get some normalized posterior. And so these should be things that are easy to compute for the distribution that we have, like Q, any Q that's in the nice distributions. And then the whole problem is that our exact posterior is not a nice distribution, or we'd be done because we could just report the means and uncertainties and we wouldn't have to deal with any of this stuff. And so the whole problem is that isn't a nice distribution. And so what are we going to do? Well, the idea of taking an optimization approach here is to say, well, out of all the nice distributions, maybe we could optimize to find the closest of them. So in particular, let's form an optimization problem. We now have a somewhat well-defined optimization problem, which is to say, let's take all of the nice distributions. Let's call that capital Q. So here, let's look at every little q distribution in capital Q and say, out of all of them, which one is sort of the least far? So here, let's say F is some notion of farness between the two distributions here. So a nice distribution and our exact posterior, and we want to minimize that. Now, there's a reason I'm not using the word distance. You might expect to say, well, we want to minimize the distance, and that's because the thing that we're going to use in a moment is not a distance. So in particular, when we use variational Bayes, typically when people are talking about variational Bayes, they're talking about F, this notion of farness, being the KL divergence. And it's not a distance because the KL divergence or the callback Liebler divergence is not symmetric. which would be one of the things we have at the distance. So let me just change this little cartoon a little bit so this isn't symmetric. This is KL in a particular direction. And in particular, when people use variational Bayes, they use KL in a particular direction, and we'll see in a moment why that's the case. Okay, so first, I think the first question we want to ask is why? Why KL? I mean, there's so many actual distances that are out there, right? Like total variation, Wasserstein, like we are not at a dearth of distances between distributions. And so surely we could have chosen one of those. Why are we choosing KL, and why are we choosing KL in this particular direction? Okay, well, there's going to be two sort of answers to that. So here I'm just going to give the sort of high level sociological kind of answer. And then on the next page, we'll dive a little deeper into the math. So at a very high level, it seems like it works. I mean, that's the real reason that we're talking about variational Bayes today. It seems like people are using it and they're using it well. It seems to give reasonable point estimates, which is something we said we cared about. You can actually use it as part of some sort of prediction environment as well, and those predictions seem to be pretty good. And of course, it's super fast. As we said, we're really interested in something that you can run in the time you have. Way back in 2013, we showed we can make it streaming and distributed and run on millions of documents in Wikipedia in about an hour. And of course, that's only been sped up so much since then. And so this is something that can really run at modern data set sizes, in modern data set problems that have very high dimensions, like for instance, topic modeling. And so it seems like it works is really the answer of like, why are we even talking about it? But now we want to kind of dig a little bit deeper and figure out, well, why is that? Why KL, seems to be useful, seems to be widely used. Okay, so in order to answer that question, so here I just have the optimization problem that we've defined on the previous page, but it's not a well-defined optimization problem yet, right? We said that we're going to minimize over the nice distributions, this notion of farness, which is KL divergence, but we need to say, what are we going to do in terms of choosing the nice distributions, and why are we choosing this farness? So we're talking a little bit more about farness. So there was a question in the chat, how do you address the distinct support issue? So with KL, you won't have KL well defined if you don't have things on the same support. Let's first actually define KL, which I haven't done yet. And then the reality is basically that, if you have something that's going to give you something like infinite KL, you're not going to choose that. Like, that's just not going to be the thing that minimizes KL. And so that's sort of essentially the question, is that, that's not going to minimize it. In practice, what happens is you just choose things to have the same support. You choose your nice distributions to have the same support as your posterior, so that you don't run into this issue. But it's certainly something to keep in mind. And actually, it's something that will come up in a subtle form as we discuss later. So it's a great question. Okay, so here let's talk about the KL. So here I'm defining the KL in the direction used by variational Bayes. So what we're seeing here is that we have the integral of our nice distribution log our nice distribution over our posterior. And for the moment, I'm just going to assume everything has densities. I mean, I think in a lot of practical problems, that's just what you're doing. And so let's not worry about, measure theoretic niceties beyond that. Okay, and now I'm going to ask a question for the audience. Yes, indeed, other divergences can address this issue, but they have their own problems. So we'll talk about that later. Okay, so let's talk about just going forward with KL for the moment. Now, before I take this step, let me note, there's sort of a weird chicken and egg problem here. So let's look at this problem. We're saying we're going to form the Q star that minimizes the KL between our nice distributions, for which we can do nice things like calculate means and variances and so on, and our exact posterior. Okay, so isn't that a bit of a problem, right? Because we don't have access to the exact posterior. So how could we possibly find the closest thing to the exact posterior if we can't even access it? And it seems like this isn't specific to KL. This is like you put any divergence in here. You put a Wasserstein, you put a total variation, you put whatever your favorite, alpha divergence in. How could you possibly find the thing that minimizes the divergence, the farness, to your exact posterior if you don't have access to your exact posterior? So keep that in the back of your mind for a moment, and let's do a little derivation, and then we'll hopefully get some thoughts. Okay, so I'm asking a real question to the audience right now. Feel free to respond in chat, or I don't know if you have the ability to respond any other way. So perhaps in chat. What did I do to go from the first line, the definition line here, to the second line? Okay, great. So Sophia said Bayes rule, and that's essentially exactly the answer. Basically, the observation here is that the conditional distribution is the joint divided by the marginal. Yeah, we got another Bayes rule. That's perfect. So Bayes rule is just a way of expressing that the joint distribution is the conditional times the marginal. And that's what we've done here. We've just rearranged this slightly and said, hey, this joint distribution P of theta and y is P of y times P of theta given y, or alternatively, P of theta given y is the joint divided by the marginal. So perfect. That's exactly what we've done here. Great. Okay, so now what have I done to go from the left-hand side to the right-hand side? Great. There's something I'm doing with the log. I'm expanding the log. And in particular, let me just go into a little bit more detail here. Basically, remember that log of A times B is equal to log of A plus log of B. And so here, A is the blue thing, B is the yellow thing. Okay, great. Let's do one more. Can I simplify this integral in any way? So I'm just interested in the first term in this sum. Great. I think you're all exactly on the right track here. So the observation is that P of y, which is you're all making correctly, is not a function of theta. This integral is over theta. And so that log P of y can come out. And then what we're going to get is the integral over q theta d theta, which folks have recognized correctly is 1 because q theta is a distribution. And so we'll just simplify that term to log P of y. And now I'm going to make one more slight change here, which is to say the log of 1 over a is equal to negative log a. And so all I've done is switch the sign and flipped what was in the log. Okay, great. So now I've got this alternative representation of the KL divergence, and I want to point out some really interesting things that have happened here. So first, notice that this first term, as you have all pointed out, is a constant, but now I want to point out it's a constant in Q. Now, if you look at the top of the page, the thing that we're trying to do, the optimization problem that we're trying to solve, is that we're trying to minimize this thing in Q. And so if we're trying to minimize this KL in Q, and this term is a constant in Q, we can just throw this term out. It doesn't matter. It has nothing to do with the optimization problem. We're essentially just optimizing over the second term. And so because all that really matters is the second term, it gets a special name, which I'll explain in just a second. It's called the evidence lower bound, or ELBO, ELBO. Now, here's the really key point that I want to point out here. We said in the beginning, we're doing this optimization problem. We're trying to find the particular distribution Q, this nice distribution, that's sort of the closest, the least far, that minimizes the farness to our exact posterior. And this is this problem that would happen with Wasserstein or total variation or alpha divergences or KL divergences or what have you, that's a chicken and egg problem. How could you possibly say what's the closest if you don't have access to the exact posterior? And here, the sort of magical thing has happened, which is now we're optimizing over just the elbow, and the elbow doesn't depend on this intractable normalization constant or integration over this intractable P. We only have to have access here to the likelihood and the prior, which we know we have access to, and the data, because that's the joint. The joint here, P of theta and Y, is the likelihood times the prior. And then the integral is over Q, which at least at the moment we're saying is a nice distribution. I haven't defined what that is, although people in the chat have accurately suggested where we might be going pretty soon. But at the moment, there's just some nice distribution, and we assume we can do integrals with it. So we have this right now. And this has gotten around the problem. We have gotten away from this intractable normalizing constant. And it's worth thinking, how did this happen? And if you look back over our derivation that we all did together just now, it seems like this really depends on using the KL. That you don't just have this pop out with the Wasserstein or pop out with the total variation, or even if you look at KL in the other direction, you don't just have this normalizing constant pop out. It really just popped out really conveniently because of the form of this divergence. Okay, so while we let that marinate for a second, let me just make a couple of points. So one, you can show that the KL is greater than or equal to 0. So basically, the KL behaves like a distance except for the symmetry and things like that. But it behaves like a distance in the sense that it is always greater than or equal to 0, and it equals 0 when its arguments are equal. And so this is an exercise that I think is worth doing in the privacy of your own time later. I think it's really good to reinforce these things. And if you get stuck in any way, I encourage you to check out the Bishop textbook, Chris Bishop's Pattern Recognition of Machine Learning. It's an excellent textbook, and it will help lead you through some ideas here. The question in the chat is, what about reverse KL? So reverse KL is definitely, I don't want to suggest that people don't touch Wasserstein or total variation or reverse KL or things like that. All I want to suggest is that you don't get this super nice simplification that we just saw here, right? So what was really nice about KL in this direction, I'm sorry, I always forget which one is like forward and backward. So I'm just talking about the other KL from the one we talked about here. When you use KL in the other direction, you'll notice the integral isn't over this nice Q, it's over the full posterior that you don't have access to. And so that's what's really challenging there. Okay, great. So because KL is greater than or equal to 0, which is something that you can all prove later, but hopefully you'll agree with me now is correct, you can immediately see from that last line that it must be that the log of P of Y, remember we called P of Y the evidence earlier, that's just a name for it, is greater than or equal to the elbow. So you just get that by saying that last line is greater than or equal to 0 and then moving the elbow over to the other side. And so now you can immediately see, where does this term, the evidence lower bound, come from? Literally, the elbow is a lower bound for the log evidence. And so, it's just sort of explaining that terminology a little bit. And so finally, the thing that we notice is that we had this original problem at the top of the page, which was we want to minimize the KL in this particular direction for the nice distributions relative to the exact posterior, and we can express that as maximizing the elbow. And what's nice about doing that is now we have put it into this form that doesn't depend on this intractable normalizing constant. It doesn't depend on these things that we can't compute, and that's kind of the whole problem to compute. Okay, and so let's just recap. What we've essentially established here is YKL and YKL in this direction. And again, that's not to say you couldn't use other divergences, that you couldn't use other actual distances, but this one is convenient. It's convenient because you get rid of that intractable normalizing constant. It's convenient because you don't have to do an integral over this, posterior that you don't really have access to. You get to do an integral over these nice distributions. And so this gives a sense of what that is. So there's a question in the chat, is why here the whole data set or one instance? We're imagining that it is the whole data set. So it's sort of like, I sort of went too quickly through that. When I said y1:n before, let's imagine that we in fact are abbreviating that as y. So it's all of the data points that we have. Another question in the chat is the other direction, EP. Roughly, there's a little bit more that goes on with expectation propagation than just minimizing the KL. There's some nuance there, but you've got the right idea. Okay, so we've established sort of YKL in this direction. And so in some sense, we've started to form our optimization problem. We want to make a well-defined optimization problem so that we can use optimization for this approximate Bayesian inference. And at this point, we've established what our notion of farness is. It's the KL in this direction. And we still need to say what it means to be nice. What is a nice distribution? Okay, so this is the setup we have so far. We need to say, what is this capital Q? What is a nice distribution? And let's again take a step back and say, well, what we really care about is being able to calculate, posterior means, posterior covariances, maybe even normalizing constants. And so when we say a nice distribution, we mean a distribution where we can calculate means and covariances and normalizing constants. Now, if you wanted to do something else, you could have a different notion of a nice distribution. That's just the one that we're talking about right here. And so let's think about it, when can you do these things? And I'd say that there are probably two types of answers to this. So one type of answer is to say, well, gosh, if I had a low dimensional distribution, I could probably calculate means and variances and so on. And so this is the idea of so-called mean field variational Bayes. Is it tries to make these questions lower dimensional questions. So essentially it says the set of nice distributions are the ones that factorize into lower dimensional distributions. So across a collection of sort of subparameters, let's call them theta j, they don't have to be one-dimensional, but they are smaller, they're sort of a part of theta, we factorize. And so you're left with lower dimensional distributions, and the hope is that those are easier to deal with. Now, a point that was raised in the chat earlier is that what really makes things easier to deal with? Like if you want to do an integral, if you wanted to do, to find a mean, you wanted to find a variance. I think the reality is exponential families are just, what makes that so much easier. And so if you look at using mean field variational Bayes in a paper or something like that, it's pretty typical that people will assume that these Q sub j's, the distributions for each of the theta j's, are in the exponential family. And we'll see an example of mean field variational Bayes in just a second. There's a question in the chat, is this somehow linked to expectation maximization? There are, in fact, some very interesting links to expectational maximization. There's something called variational EM. I'm just going to leave it at that and say, if you're interested, look up variational EM. There's also a really nice paper by Turner and Sahani, 2011, that I'll mention later, is also sort of goes into this link. And I think the Bishop book probably does too. Okay, so a super important point here is that this nice distribution idea is not a modeling assumption. We have not restricted our model in any way. And this is really important, because what we really want to do in Bayesian inference is we want the scientist, we want the engineer to come up with a model that represents like what is actually physically going on in life. Or we want the social scientist to come up with a model that represents what they really want to get out of their social science experiment. And we want them to just do that. And now we want to find the posterior or some approximation of it. Now, this is a little bit idealistic, but like that's essentially the workflow that we're aiming for here. And so we don't want to restrict the models in any way. And at this point, we haven't. We're just saying all we do is restrict the assumptions. We restrict what we can approximate the models with. Now, that doesn't mean the approximation has to be good, and that's really the question that we're going to be asking going forward is it a good approximation? But we haven't restricted the models. And we'll see an example of that, and hopefully some things to drive that home in a second. And so just to anticipate where we're going here, let me just sort of give this example of here is a case with an exact posterior that does not satisfy this mean field assumption, because we wouldn't in general want to restrict our model to satisfy it. It would be way too restrictive. But our mean field variational Bayes approximation is nonetheless a pretty good approximation. It's sort of weird. I mean, it feels like this is like a really huge approximation to be making, and yet the mean and variance of this approximation look pretty decent. Okay, so now we have an optimization problem. We can ask ourselves, how do we solve it? And this is, again, something that I'm kind of going to table. I'm going to say there are lots of really great ways to solve optimization problems. This is a whole field, in modern machine learning, is how do you solve optimization problems? We're going to talk a little bit about coordinate descent, that you could go through each of the Qs and solve them. And we just know in modern optimization that that's not really the best way to go about doing things. So this will be more illustrative than me telling you that you should definitely do coordinate descent. Like you should really use whatever is a good optimization algorithm. But this is one thing we'll use for illustration. Okay, so before I go on, I just want to recap where we are at this point. So we have said we want to do approximate Bayesian inference. We have this posterior, we want to approximate it, and we're asking, how are we going to do that? And so we started by saying, hey, we're going to make a choice. We're going to use some Q star to approximate our posterior. Now, technically speaking, like going in, we don't necessarily have to do this. If all we want in the end is an approximation to the mean and variance, or means and variances of this approximate of our posterior, maybe we don't have to go through an intermediary Q star. But this is a choice that we're going to make here. Now I'm going to go and sort of make a Venn diagram of approximate Bayesian inference. Within this, we're going to make a further choice. We're going to choose to optimize. Now, we don't have to do this. There are other ways to use a Q star to approximate our exact posterior. We could use a Laplace approximation. We could use Markov chain Monte Carlo. And that's not the direction that we're pursuing right now. We're pursuing an optimization direction. And in particular, we're pursuing this particular optimization direction. We're saying, let's minimize over the nice distributions some notion of farness. And then we made another choice. We made a choice, which is, what is the notion of farness that we could use here? Again, that's not the only possible choice. We could use total variation. We could use Wasserstein. We could use alpha divergences. There are so many other things that I'm not even mentioning right now. There are lots of choices, but this is a choice that we're using. Yes, so there's a point in the chat that this assumes the model is differentiable, and indeed, a lot of modern methods for approximate Bayesian inference assume at least some form of differentiability. You'll see that in MCMC as well with things like STAN. And it's an interesting thing to ask sort of how does this limit you and how doesn't it? But we are going to be assuming, again, things like densities. You have to be a little bit careful about what's differentiable and what's not, because we are allowing certain types of, things like discrete variables. But there is a certain notion of differentiability that's assumed in a lot of these things. Okay, so now beyond variational Bayes, we're going to make this further choice of what's a nice distribution. This isn't the only choice of nice distribution that you could have, but certainly it's a very widely used choice. If anything, I think that typically when you read a paper, they're going to be using mean field variational Bayes if they're using variational Bayes. And then finally, we can ask what types of ways we could optimize this. And there are many choices. There's coordinate descent that's, again, usually sort of mostly used for illustration. There's things like stochastic variational inference that make this very, very fast to use on large data sets. There's things like automatic differentiation variational inference, and certainly this assumes certain forms of differentiability in order to use automatic differentiation. And this is very black box, and it makes things sort of easy to use in practice. Okay, so what I want to emphasize here is that we've made a number of choices, and these aren't the only choices we had to have made, but they're particularly popular choices, and so we want to understand how do each of these choices affect our approximate Bayesian inference. Are they good choices? Should we have made different choices? What are they doing? And it's worth separating out each one too, so we know if we want to change something where that's going to be impactful. Okay, I'm going to make a quick observation, and that is, what is variational Bayes? And I think the reality is that you may find that this varies a little bit from paper to paper. So the words variational Bayes essentially in some sense come from sort of calculus of variations. So, sort of we have this optimization problem of functions that we're optimizing over functions, and so that's where calculus of variations comes in. You will find in papers that sometimes when people are talking about variational Bayes, they're talking about it at this level. Sometimes they use the term variational Bayes to refer to any optimization problem of this form. And sometimes they use the term variational Bayes to refer to mean field variational Bayes. So in all of these cases, the reality is you always have to check what is the paper actually doing. When they say they're doing variational Bayes, hopefully they spell it out somewhere. They say what exactly is their optimization problem, and then you know which one of these we're doing. Okay, so this is the setup. This is what we're doing today and in the following steps in terms of not just approximate Bayesian inference. This is sort of the realm of approximate Bayesian inference, but variational Bayes in particular within it, and mean field. And so I think that we're just about out of time. And so I will leave for our next meeting talking about why use variational Bayes. So I think very reasonably at this point, you could say, well, why would I expect minimizing the KL to be useful at all? Why would I expect this mean field assumption, which seems really, really stringent to be useful at all. And so we're going to walk through some examples of using this in practice next time, and basically see that it's, perhaps surprisingly can work really well. But then again, beyond that, we're going to talk about, are there pitfalls? Are there places where it doesn't work? And I think the reality should not be surprising to anybody who's done anything algorithmic whatsoever, that of course there will be pitfalls, and we just need to know what they are. So I think that that we are out of time for today, is my understanding. So I'll leave it there. Again, I just want to mention, I'll have these slides up on my website. I'll also share them with the organizers here. And I encourage you, if you have some time before tomorrow, to consider running through some of those exercises, because I think that can really help solidify some of these ideas, and get us ready to discuss sort of using this in practice. So the question was, where will the slides be shared? And so I shared a link at the beginning, but I should have shared it again here. So if you go to tamarabroderick.com, there'll be a tutorials page there, and I will put them there. And I'll also share them with the organizers, so they may well be shared on the summer school page as well. Great. Okay, thanks, and I guess I'll see you tomorrow.